So next up is Gnark on ice, ZK acceleration in Golang using Icicle by Omer Shlomovits at Inganyama.
Thank you. So for those of you who've joined, and by way of introduction to the company, I want to present to you a sneak peek into the first ZK movie. Okay? Go ahead.
Modern stock markets, information has always been our most valuable currency. Today, general information is easily accessed and personal information easily shared with the world at our fingertips. The need for trust can be an unnecessary obstacle, slowing the pace of progress. Zero-knowledge proofs remove these obstacles, as they remove the need for sharing trusted information that could be leaked or lost, eliminating the risk of attack or exploitation. Zero-knowledge has the magical ability to guarantee data integrity and removes the need for storing and keeping track of users' information, reducing costs and freeing up resources. And it doesn't stop there. Zero-knowledge technology is applicable to any field where trust is involved and will revolutionize how we interact with countless domains. Inganyama develops cutting-edge hardware necessary to make this technology accessible for all.
All right. Full movie is coming soon. This was just the trailer. No, seriously. It was done, by the way, with generative AI. If anyone wants to learn more about it, please find me afterwards. So yeah, let me start with the motivation for this talk. Few facts, okay? So first, snarks are slow, okay? Let's acknowledge it. Proof generation is quite slow to do. This is like very natural. It's part of the trade-off space. So we need to deal with it. The second thing is that modern snark frameworks, right? So we're going to talk about Gnark, but also Halo 2, ArcWorks, Rapid Snarks. Natively, they support CPU and CPU alone, right? It makes perfect sense. This is how we start when we build software, but that is the case. Third, hardware accelerators are very accessible, right? They are cheap. Cloud, gaming GPUs, right? So they are here. Fourth, we know that from experiments that were conducted publicly and like results were shared, such as zkParis, we know that we can take primitives that can be found in zero knowledge, in snarks, and accelerate them using specialized hardware. Therefore, the conclusion is that we should try to merge these two things, right? Let's bring zero knowledge accelerators into these frameworks, these Gnark frameworks, okay? And today I'm going to talk about one kind of integration that we've done and share some of the insights and results that we've seen on how it works. Obviously, spoiler, it works nicely. So before jumping into that, one previous attempt that kind of led us to where we are today was an experiment we've done jointly with Geometry. And back then we took ArcWorks, so another ZK framework. Specifically, we targeted Golang 16 and BN254, which is the same kernel protocol we're going to use also for this talk and today. And we used the FPGAs that can be found in the cloud, right? So it's like the same kind of like accessible hardware. And we just took the MSMs, right, the G1 and G2 MSMs, and basically moved them to the FPGAs. And you can see that for different number of constraints, we actually get some performance boost. It is not much, but it gives you kind of like the hope that something can be done here, right? Maybe more professionally. One thing to note is this like component called SparkWorks, which was designed or something that we noted that was needed to kind of like make everything very clean in terms of API. We want the hardware to be indifferent to the exact protocol and framework, and on the other end, so that we can like switch hardware, and on the other end, we want frameworks to kind of like be insensitive to what hardware they are running on. So it should be also very simple. So now let's kind of like take this idea to the next step, which is kind of like productize it in a way. So the idea is high-level API that would allow developers, whoever they are, to add this dimension of GPU acceleration to the work they're doing on whatever ZK application that they are developing, okay? So here, of course, we need to target real-world circuits, so it's not just like an experiment, let's do something that actually can be used. And we do need to kind of like, I guess, evolve this SparkWorks to some library. So this is what Icicle is going to be about. And we've done this kind of switch between FPGA to GPU for several reasons. GPUs basically are more commoditized, very easy to program, so the cycle, kind of like the iteration, can be quicker, and they actually provide better performance. Although, I mean, that's a point to discuss. But let's assume that they are a very good candidate for this kind of like goal. Okay. So as I said, today I'm going to talk about Gnark and Gnark ZK framework. So let's give a bit of background about that. So it's a very fast library. It's ZK Snark library that is written in Go, okay, Go language. As you can see on the right, this is a benchmark that was done by Seller team, and excluding the outlier Starkey, which, you know, it's kind of like a different place on the trade-off space, you can see the Gnark is very, very efficient compared to other frameworks, right? So we wanted to aim high, kind of like start with the best there is. Gnark supports Gold 16 and Plonk. You can see that also they have a very, very clean and easy way to kind of like use the library. And we specifically, for the sake of this talk, but of course it's going to work with every circuit, we used Seller circuit, actually the old version of it, for BLS6, so just like, you know, many signatures. And again, we use Gold 16, BN254, and something that is a bit more than 2 to the 23 constraints. So it means that when it comes to entity, you need to kind of like count it to 2 to 24. We'll see more about it soon. Okay, so I mentioned Gold 16, therefore I should probably give some relevant background. So Gold 16 is this ugliness, okay? Luckily, today we don't need to actually understand everything that's going on here. We need to focus just on the prover. Remember, this is the part of the trade-off space that we care more about, so double-clicking on that. And this actually, by the way, this is a diagram that we have in the company, kind of like helps us to you know, make reason with Gold 16. So you can see there's a nice division between step 1, which is the quotient polynomial, and step 2, which is kind of like where ellipticals becomes more kind of like to finalize the proof. And you can also see it also kind of divides nicely between the heavy operations, the entities, and the MSM. Okay, so you can see that in the quotient polynomial, we have several FFTs, and on the other side, we have MSMs, okay? Again, these are like the heavy lifting or the computationally heavy parts of Gold 16. And obviously, the immediate target for us to move to the GPU. So let's do a proper breakdown, okay? So as a matter of fact, we have 5 MSMs and 7 entities, or 1 MSM is in G2, so it's a bit more expensive, like 3x, okay? It's like an overextension field. And entities are actually like 4 of them are I entities, okay? Now, one point to note is that MSMs, you can see it from this like diagram, can basically be run in parallel, okay? So there's no really dependency between them, which is interesting, and I will address it later. About the entities, so there's something here also kind of that is hidden, and this is that entities should run or should be using something we call like twiddle factors, and also like they can run on the coset in sometimes, and basically we kind of like ignore this the time to generate those. We just assume it was like pre-computed and was like already loaded to the device GPU memory, okay? Finally, and this is an important point, is that there is an interesting distribution, and when we move into a real-world use case or applications, you see that there are like interesting distributions of the MSMs, okay? So some of them are easier to handle, like zeros, like ones. Some of them are more tricky, and I'll talk about it in a few more slides. All right, so now let's talk about what exists today in Gnark in terms of CPU acceleration, okay? So we have a few levels of acceleration. First is the parallel execution of MSMs. As I mentioned, they can run in parallel, and you can see on the table on top that the MSM total time basically takes the same or roughly the same as the most expensive MSM, okay? So that's kind of like a high-level nice trick, and obviously it works when you have, like, this is a very powerful CPU, by the way, which we took for like our tests here, 24 cores and so on. So yeah, you can take advantage of that. Lower level, you have some primitive level acceleration and parallelization, and this happens in another library called Gnark crypto. Okay, remember that. And here, both for MSM and NTT, state-of-the-art algorithms are being used. Buckets method, also known as Pippinger, and they take advantage of some multi-threading. Okay, at different levels. So MSM bucket method is very, it's like embarrassingly parallelizable. With NTT, it's a bit more challenging, but still, there's some kind of like go-routines that help you do that. Now, the other part I need to introduce to you is Icicle, okay? So what is Icicle? So this is a library for zk acceleration using CUDA-enabled GPUs, okay? Now, the idea is that we want to move as much as we can to the GPU, right, to the device from the host. We have two APIs at the moment, right? So we have the Rust API, and now we also have Go API, and basically the design, we have two like levels of this like API. So one of them is higher level, like you can imagine facing developers, where you can do polynomial arithmetic, some operations like interpolation, polynomial multiplication, and so on. And there's the low level API, MSM, NTT, and such. And I will show you very soon why we need both of them. Okay, it will make sense. And other than that, we do have just like a lot of calls to GPU functions, which are called GPU kernels. Now, the library supports, again, vectorized arithmetic, as I said, MSM, NTT, polynomial arithmetic at the higher level, some hash functions, and some like complex structures like ECNTT, which is basically NTT, but coefficients are elliptic curve points, batched MSM, like many small MSMs that run in parallel, a Merkle tree, and so on. One reference application that we developed ourselves is for fast dunk sharding. Obviously, Gnark, it's like it's not us, it's like built on shoulders of giants, and we just like use this library here to help introducing GPU into these frameworks. So now that we understand the components, let's understand the architecture, which is very simple. This is like the goal here. So on the host side, we had before Gnark and Gnark crypto. Remember, Gnark crypto is where the MSMs, the entities, are being actually implemented. Now we, inside of Icicle, first we have the API, which is called what we call Go Icicle, and second we have the actual like CUDA and calls to the device itself. And to switch between the two, we have this kind of like flag, right? It's very simple, should be very easy. For a developer point of view, you don't need to think about like I'm working with GPU or what do I do? We just need to say I have a GPU, I want to support it, right? Very simple. There are two trade-offs that I want to just mention quickly. One is about utilization. So one point to consider here is that once you go to GPU and you get the GPU to become busy, CPU becomes idle, right? So this is something that we might want to take advantage of at some later point, because when you work only on CPU, you can get like 100% utilization. So we want to make sure that we are not like losing anything there. The other thing is about power considerations, right? So GPU introduces another device, it has its own kind of like power consumption that needs to be taken into account when you look on your like application and end-to-end solution. Okay, so now let's start to understand how we do the integration itself. So obviously the first step, as I mentioned, is just do a true pin replacement. Let's take the MSMs, let's take the entities, and let's just switch, right? Before we had Gnark crypto, now let's call Go Icicle. Problem. Here's an interesting part of the diagram I showed you before. So as you can see, on top we have FFTs, and these FFTs are on green, they are executed on the device. Then we are sending them back to the host on red, right? Then we do this kind of like polynomial operation, this vector operation, right? So we need to compute the points of H tilde, and then we send it back to the device, right, for the IFFT. Now, what happens is that these data transfers actually take quite a lot of time to do, like compared to the computation itself. So we want to eliminate those. So the solution is very simple, and this is exactly what Icicle helps you to do with this like higher level API. We just move this like part of H tilde also into the GPU. So now we actually managed to save on this like back and forth between the host and the device. There's actually a few more benefits on doing that. One is that H is actually it's embarrassingly parallelizable. So as you can see below, we kind of like eliminated completely the running time of this like computation, what we call the polyops. And also, we need to account for the fact that it might be that for GPU, we do some kind of like conversion, or we like more to work with some kind of like coordinate system, or do some kind of like different multiplication than the representation that happens at the host, or like some framework decides that it's the best decision for it. And we can save that as well by kind of like staying in the GPU. Okay, so now let's talk about performance. And for the sake of this specific example, I'm using RTX 3090 Ti. It's like last generation GPU, but still starting with the entities, okay? So what we realized is that, well, in the CPU, running entities was done in serial. This is what made more sense here. There's actually a higher level parallelization that can happen, right? So we can run this FFT pairs. You can see it like the LRO together. And if you actually want to get to this like bottom, like, you know, the 441 number, you need to kind of like take the most expensive pair and add to it the IFFT and some kind of like time it takes to kind of like move the data that is not really represented in the table. But it's nice to know that like the design space changed a bit, right? Once you move the entity to the GPU, all of a sudden, it's not just a different algorithm, it also makes sense to kind of like change the parallelization, right? To fully utilize the GPU. With MSMs, so here on the other end, while on CPU, it made more sense to run them in serial, in parallel, here actually it makes more sense to run the MSMs in a serial fashion, okay? So why is that? I'll touch a bit on that later, but basically it has something to do with how we utilize the GPU. If the GPU is already like fully utilized with one MSM, like adding one more and adding another MSM in parallel won't help us, okay? And here, just for like sake of clarity, I've kind of like made this table for translation to kind of like show that like there is how we define our MSMs, like, or how we code them, and there's how they are called in Gnark code. There's also some kind of like theoretical understanding of the size of those, and also a lot of filtering that is happening, which is very interesting to notice, but I won't have enough time to go into the details of why this is what happens in real life, like code 16. Finally, there's some kind of result, and what I want you to take from this is that, I guess this is like 3-point-something x. I think that today we have like, I don't know, like 6x or something or more, but it really depends on the problem that you're trying to solve. So remember, right now we used a very powerful CPU, also like last generation GPU with certain parameters. It can be very sensitive to how we choose our setup and what we are trying to optimize for. And to make this point, again, so let's look on CPU 1, which is the one we just used, and we can see the total power time below. Now I'm going to use another CPU, CPU 2, which is even more powerful, right? More cores, higher clock, and so on. And you can see to get a better proving time overall. I'm going to use now CPU 3, which is much slower, okay? So you see it's lower clock, although like number of cores is quite equivalent. This is Xeon server. And you see that like proving time like jumped. And on the other hand, now with my previous result of CPU 1 and GPU 1, we can get much better if we go into CPU 2 and GPU 2, which is, again, just like newer generation, still less string processing elements, but higher frequency. So it's really up to what is your design goal, where you want to get. And it's important to note that like, basically what we've done here is we added something to the design space. Now, if you have GPUs, you can kind of like, I don't know, think a bit more holistically on your entire like application and how you want it to run. Final like departing thoughts on like implementation details and future work. So first, I think it's worth to mention how the MSM works in the GPU. So this is like a trace from like a tool that's provided by NVIDIA. I think the main point here, it's like first, no secrets. I mean, this is just an MSM like buckets algorithm. It's more or less what you had like as the winner of zprize. Okay, so it's kind of like the same. You can ignore the green part. It's like just copying stuff to the device. Again, like we've done it like way before. This is just like taking one simple MSM. What's interesting to note is that most of the time spent in the GPU is like on this like, you know, step where you need to accumulate and do many EC additions in different buckets in parallel, right? You see it here, we spend a lot of time. Now, I do want to point your attention to one important detail that is not present in zprize, which is this like non-uniform distribution, okay? So basically what you can see here in all of these traces, like on the top, you see what happens when you have uniform distribution, okay? So this is how we think about MSM algorithms. Originally, you want to say, okay, like let's say all the points are, and the buckets basically have the same size, which is very important for GPU, because remember in GPU, we basically take advantage of parallelism and you want everything to run in parallel and end at the same time. It's critical. However, what we see in practice is that there's highly skewed distribution and not non-uniform distribution, and we need to address it. So if we just use the naive, it's not naive, but like the uniform algorithm for this like distribution, we get much, much worse times, okay? It's important. And this is also after we do the like basic filtering of, let's say, removing zeros and like computing the ones like someplace else, okay? So what we actually managed to do here to answer for that is tell the GPU to basically first do some kind of like sorting, understanding like the different, or understanding the distribution of a given circuit on the fly. And then we take the heavier workload, the heavier buckets, and we move them into a different kernel function, which has more threads allocated to it, so that eventually they can end at the same time, which for that we use something called streams, okay? So you can see that we are kind of like get back the times that we had with this bucket averaging, we get back the time of the uniform distribution, okay? The second point I want to make is that, as I mentioned, today, the MSMs, at least for this type of circuit, but remember, this is just an example, the MSM fully make the GPU fully busy, like it saturates the GPU. So, and this is just the numbers, you know, it's just to show that we need so many more threads than what's available. Basically, what it means is that if you want to add more GPUs, you can cut the time, right? Like 2 GPUs would cut the time in half. Finally, there are obviously some points to improve. Some of them we already improved. Compared to zParis, our EC addition, modular multiplication, like something that can probably be optimized. There is the thing about utilization of CPU. So basically, CPU is free for a lot of the time. So we've noticed that moving stuff back to the CPU and running it in parallel to the GPU actually takes a nice advantage of the entire setup. So this is important, right? So as I'm saying, try to look at it as kind of like we add more dimension to the design space. Yeah, and finally, there's some kind of like different like, you know, components we can move and kind of like also optimize a bit more. I think I'll stop with that. Happy to take questions, and obviously big shout out to the Gnark team for all the help and working together on this. It was great. Amazing experience, and you are also free to use like the libraries open source MIT Icicle. It should like you don't need us, just use it. You have the API. Would love to help. Thank you.
Have you done any exploration on hardware acceleration for witness generation?
So I didn't get the question.
So have you looked into using hardware acceleration for witness generation?
Oh, okay, thank you. So have we looked into witness generation? So I cannot say that we've looked at it, definitely not like at the level that we looked on proof generation. It's definitely an open question, at least for me and my team. I think in general, like the point I'm trying to make here is that let's introduce GPUs and let's see, and you know, like improve the infrastructure overall. And I'm pretty sure that witness generation can also benefit from it. Remember that we can also like make some impact. I mean, on the protocol designers, like maybe there are like some, you know, best practices that can happen on how you do the witness generation. So it's like for me a very kind of like open question. Like, would love to explore it at some point.
Hello. I didn't fully get how you solved the latency bottleneck in terms of data transfer. If you could quickly go back to that. Sorry.
You mean this one?
Yes, yes.
So again, just like quickly reiterating, we have here 2 parts. Like we just moved like, naively to GPU the entities, but it caused us to have this like annoying computation stuck at the host side that now we need to address. And it means that you need to take all these like big vectors, like large vectors from the entity result, like, you know, back to the host, and then from the host after computation back to the device. That's an issue. The simple solution is to call the GPU again, but you're not really going outside of the GPU. You call the GPU staying on the device, right? You just like, make different commands on how you want the GPU to be used. So just like invoke a new kernel, a new function that basically does this like in parallel, this like computation of edge, and then like you keep everything in the GPU. So you don't need to go back to the host.
Thank you.
Thank you, and wait for the full ZK movie.